So this week, Jayanth from the TFA team has come to present the session about feature detection mechanism. So without further ado, I'll hand over to you, Jayanth.
Okay, thank you. Hello, everyone. Thank you all for joining the presentation today. Well, a quick introduction about myself. I'm Jayanth Chidanand, software engineer in TFA team from ARM. So I'll be presenting today about the feature detection mechanism, what it is all about, the design, the implementation details, and everything. So a quick note, if in case at any point of time, if my voice is not audible or if in case if the voice is broken, please do stop me. I will be happy to repeat the things. So having said that, let's get started. So this is the agenda for the presentation today. I will be briefing you about what this feature detection mechanism is all about and why we actually implement this mechanism, what was the requirement, the design we have followed, and the implementation status so far, and some of the blockers, what we have faced when implementing this, and a quick note to the partners, what they need to be aware of, and the future scope, what we are planning to do ahead. So moving ahead. So yeah, the first question is, what is this feature detection mechanism is all about? Well, as the name suggests, it's just we are trying to identify the features, that is the architectural features, which all have been implemented in TFA, whether they are properly been enabled or not. Meaning, usually we have a build flag for each and every feature. So usually we enable them during compilation. So we need to ensure that whatever the flags which has been enabled, have them, or are they enabled correctly, or they're matching with the hardware as well. So with this mechanism, we can quickly get to ensure that whether they are properly enabled or not. If not, we will be providing with some error logging support and we will be stopping it at the boot time itself. So I will be explaining in detail about how we are trying to achieve that. So what was the need for this feature detection mechanism? Why we actually landed up here is, well, usually during the context management phase, previously we were actually, saving and restoring all the registers, the system registers during context management. And this was based on the architectural version. But ideally speaking, the registers, whichever we are saving and restoring, they are more tightly coupled to the features than the architectural version. So I will explain you with a code block in the next slide, but just before that, so giving in a quick recap, what actually went wrong. So for a given version of architecture, usually the registers will be more influence, they'll be under the influence of the optional as well as on the mandatory features. But there are some certain scenarios wherein for a given version of architecture, both of them will not be present. So under such scenarios, if we try to access such registers, which are under the influence of both mandatory as well as the optional features, we will lead to some, that leads to some crash or some exceptions during runtime. So in order to handle these kind of scenarios, we thought of removing the redundancy, dependency on this architectural version macro. So this is the code snippet which we had, in our TFA code base. So during the runtime, we usually, during context management, we usually save the registers. So previously we were using this ARM architecture list macro. Let's say, for example, if we build TFA for 8.6 version and during runtime, we will be saving this set of registers. So what happens is, taking this as an example, hypervisor activity fine grained trap registers. This register is basically present only when feature AMU version 1 as well as feature FGT both are implemented. And this is as per the ARM. So if in case if both the features are not present in the PE, the direct access to this register is an undefined behavior. So what would happen is, let's say if we have built the TFA for 8.6 during runtime, we will go and access this register. But internally what's happening is feature FGT is mandatory for 8.6, but not AMU V1. So in this case, we are, accessing this register, we are actually unconditionally, we are accessing this register. So in order to remove this kind of check, unconditional access, what we thought was we have to handle it in a better way rather than depending on the architectural versions. So one way, what we thought to handle this is, instead of having this ARM architectural list macro wherein we are considering the architecture version, we thought of introducing feature-specific build flags, having one specific build flag for each and every feature, and then provide controlled access to those registers, something like this. So during both save and restore routines, instead of directly accessing them using this ARM architecture list macro, we introduce this feature-specific build flags. So in this way, when the platforms or the users, whenever they properly set the build flags, then only there will be access to these registers. or else there won't be any access. So in this way, we can avoid the runtime exceptions. So this was one way to handle this, but this was not the complete solution, because one of the advantage of having this build flag from the ARM architecture list macro is obviously, yes, we were we were able to avoid the exceptions. And also the advantage was we were not doing any dynamic feature detection, meaning we were not reading any ID registers to get confirmed whether the feature is present or not in the PE. We were just going with the build flag. So we were, more confident that the platforms will be more aware that when they're going to enable this build flag, they will be aware that PE actually supports it. But still, this is once again, there is some room for the errors. Knowingly or unknowingly, still the platforms or the user may unknowingly may enable the build flags, which is not, and that build flag might not be valid. Meaning, this is just a build option. We need to validate this build option as well in order to ensure that there will be no errors in future. Completely, there should be elimination of these errors or the runtime exceptions. So in order to handle that, what we thought was we need to validate this build options, and then only we have to access these registers. So that is where we landed up in feature detection mechanism. So in feature detection mechanism, how we are trying to achieve that, I'll be explaining in the next slide. So moving ahead, what this feature detection mechanism is all about, we'll be basically validating this build flags at an early phase, that is during boot time. And then based on that, we'll be making use of these build flags at the later sections. So I will be explaining in the next slide about the code sections where exactly this build flags will be utilized. So one thing is we will be validating these build flags by reading the ID registers. So whichever build flags has been enabled or been set from the platforms or from the users, during boot time, we will read the ID registers which are specific to that particular build flags. And then we will get verified that, okay, fine, that particular feature is present in the PE. If not, we will be stopping the booting at that moment itself. We will not proceed till the runtime and then see the exceptions at the later part. We will try to avoid we will try to prevent the exceptions at an early phase. So in order, but again, reading these ID registers all the time is not a good approach, because obviously during runtime there will be a lot of context management will be happening from EL2 to EL3 and vice versa. So every time if we keep on reading the ID registers, that will be an additional overhead. So again, we thought of simplifying this, wherein instead of reading the ID registers every time, let's bring this particular mechanism at a common place, wherein at one time we will read through all the build flags, get it validated, and then if all the build flags which has been set from the platform, it is valid, then only proceed to the next stage. If not, during boot time itself, let's stop the boot flow. Let the platform be aware that, okay, fine, whether they have set the build flags properly or not. So in one way, we can consider this kind of a diagnostic tool, wherein we can assure that whether the build flags has been set properly or not. So moving ahead, the design, what we have followed this time is, we thought of considering a tri-state approach for the feature enablement from EL3. Meaning, so far for each and every build flag, we used to provide only two options, that is 0 or 1. Either disable it or enable it. From now on, we thought of introducing another state called state 2, wherein apart from 0 and 1, we'll be introducing one more state. And the reason I'll be explaining ahead. So, but before that, the meaning of the states, yes, when the flag is set to 0, it is obviously disabled, nothing changes here. When the flag is set to 1, from now on, there will be some hard check happening at the boot time. So that means the software and the hardware has to match 1 to 1. I'll explain with an example with a feature. So first thing is, if the feature is set to, if the feature flag is set to 1, there should be 1-to-1 match, or else the panic will be called at the boot time itself. So we will be stopping the boot flow at the boot time. And if in case, if the feature flag is set to 2, here the feature enablement will be happening, but this time there'll be no panic or any stopping in the boot flow, but we will try to avoid the exceptions during runtime in an other way. So how I will be explaining that. So this is how we will be, we have implemented this feature detection mechanism with 3 states for each and every build flag. So yeah, this this table will give you a better picture. So we have considered 3 states. So this is where, mostly we'll be using our build flags during context management sections. So if in case, if the feature state is set to 0, let's say, for example, feature FGT, if the feature flag is set to 0, what would happen is, I mean, nothing changes all these three sections. So it remains disabled. If in case if it is set to 1, what would happen is the feature check will happen during boot time. That means in the boot section, usually at a BL31 main, in that .c file, what would happen is we will check which all features have been set, and we will verify whether that particular features are present in that PE or not by reading the ID registers. If in case if any of the features are not present, we will call panic and we'll stop the boot flow at that moment itself. We will not allow the platform to boot ahead. So if in case if all the features which has been set from the set by the platform is valid, then we will, and if this particular section passes, then in the next subsequent sections, that means during context management as well as in save and restore routines, we will be very much assured that all the build flags are valid. I mean, they are properly set. So here in these two phases, we will be not doing the, I mean, we will be not reading the ID registers again and again. So in this way, at one point of time, we will be getting validated of all the flags. And in subsequent sections, we'll be just using the build macros to guard the access to those registers. So the only I mean point to keep in mind here is this is kind of hard check. So there will be panic will be called and the boot flow will be stopping here. So this is kind of the order of strictness will be more high here. And the next state is state 2. So here what would happen is if in case, for example, if I set the FGT build flag to 2. So here during boot phase, we don't do any check here. So we will allow the platform to boot. We will be not checking whether the features are present or not. But during context management and save or restore routine phases, we will check the, I mean, we will be reading the ID registers, and then we will be ensuring whether we need to enable the feature, and then whether we need to save and restore that particular registers. So yeah, I mean, this comes with an additional, I mean, overhead wherein we'll be reading the ID registers again and again. But this has some particular use case. So I'll be explaining further. So if you see when altogether in general, so the order of sequence is something like when the feature is disabled, it's very low. So when the feature state is set to 1, it's a
Ouais, je suis à la rue pour changer le sort de sujet. Oui, oui, bah écoute, on sera.
sorry, sorry, it was not audible. Could you please repeat? Hello. Hello.
Might have been a mistake.
Okay, fine. Sorry. Then I'll proceed then. Sorry then. Yeah. So yeah, just coming and repeating again. So the order of strictness is in such a way like when the feature state is set to 0, it's a low order. When the feature state is set to 1, the build flags will be strictly checked. That means the hardware and software should be matching 1 to 1. And when the feature state is set to 2, I mean, the order of strictness is medium. So we will allow the booting, and then during runtime, we will do the checks. So moving ahead, what are the pros and cons of this mechanism? So what is the advantage with this compared to the previous approach? I mean, in the previous approach, we just introduced the feature specific build flags. We did not do any additional checks there. So with this approach, obviously the advantage is like we are getting ensure that all the build flags are validated. They're not just set by the user. We are also ensuring that the flags are set properly. And then also the next thing is we are providing the flexibility for the platforms to fine tune this mechanism. The thing is like, obviously there are certain situations wherein there will be multiple variants of a particular platform. So we want to provide a software in such a way like in the single set of software, I mean, single version of software, the platforms should be able to run on their multiple variants. So with, I mean, this they can achieve with the help of feature state 2. But if we don't introduce this feature state 2 with the feature state 1 alone, they will not be able to achieve this because with the multiple variants, in few variants might support few features and few variants might not support others. So if we don't introduce the feature state 2, as I said, in the feature statement, there should be 1-to-1 match. So there will be boot flow will be stopped. And as a result, the same set of software will not be running on multiple variants. So this was one of the main reasons to introduce this state 2, wherein the platforms can then decide and they will be having more flexibility in I mean, fine tuning this mechanism. So, and also that software will be more dynamic rather than very strict checks happening with the state 1, what's happening there. So the platforms can decide whether they want the very optimized software. Then when they're pretty much sure that they are only using one version of their platform, they can straightforward go and set set to 1 for all the features. If in case if they want more flexibility, whether that means the software should decide on its own rather than they deciding it, they can just proceed to set it to 2, so that the software will decide during runtime and that means the boot flow will not be stopped there. So yeah, I mean, the only cause is like, the software will be relatively less optimized due to the more conditional checks during context management and during save or restore routines.
Hey, Jayanth.
Hi, yeah.
Quick question.
Yeah.
Did we do any measurements of how much slower is state 2?
Currently, we haven't done so far. So I will explain till what stage we have reached now and what is our plans for the state 2.
Right. Maybe I was thinking, I mean, I find that TF is usually underutilized. Maybe something there could help in future as well.
Okay.
Just an idea in terms of measuring the difference between these.
Okay, sure. I will consider that point, sure. Yeah.
Thank you.
Okay. So moving ahead. So yeah, summarizing all together, these are the key features of this mechanism. So right now we are introducing this with a build option. So we allow the platform to enable this entire feature detection mechanism by providing a build flag so that they can enable it or disable it based on their requirements, because it's kind of diagnostic method. So they can make use of it. And we are introducing it with a tri-state approach. So we allow the flexibility to fine tune based on the requirements. And one more thing is we provide the support for both the debug and release builds. So instead of assert, we are introducing the panic option so that it can support for both the debug and release builds. And finally, we provide some minimum error logging support. If you could see this picture, for example, this is how we are, indicating to the user that, okay, fine, feature SPE is not supported by the PE, so it will stop during boot time. The panic will be called. So in this way, the users will be getting to know that, okay, fine, they have by mistakenly set this feature, or they will get to know that, okay, fine, the PE is not supporting it, they have to disable it. So this is the key features of this mechanism. Moving ahead. Now coming to the, okay, till now we talked about the design part. So now with the implementation, as I said, we have introduced a tri-state approach. So in the implementation, we have divided the entire thing into 2 phases. In phase 1, wherein we have covered feature state 0 as well as 1. And in phase 2, we are planning to cover the feature state 2. So right now we are in the phase 1 delivery. So that means we have covered the feature state 0 and 1. So giving you an example with for a particular feature, how we have actually implemented this. So let's take, for example, HCX feature. So what we usually do is for each and every feature, we provide a build flag so that the platforms can decide to enable or disable based on the requirements. So what would happen is, let's say if the feature, if this flag is set to 1, what would happen is, so there is a particular loop, a function which basically loops through all the features which is being supported by the TFA. So, and in this function, we will check which all features has been enabled. So assuming that this particular feature has been enabled, so it will come here and it will go through this function. It will check, okay, fine, it has been set to 1. So here we will read the ID registers, and if in case if the PE supports it, not an issue, that means this particular function returns success. So that means we'll be proceeding ahead. So it will be looping through all the features which has been supported by the TFA. And if this particular feature returns success, that means whatever features has been enabled, it's been properly enabled, no doubts there. So let's move on. We will be very much sure that in the next subsequent sections, we can use those build macros without any kind of hesitation or any confusions. So assuming this, taking this as an example, so HCX is being verified here. It will be detected in this function. So if in case if it is present, so in the next sections, because this will be running at only one place, that means during boot time, but these 2 sections will be coming across multiple times during the runtime. So here we don't want to run this set of function. So that's why we will be bringing this set of functions wherein we'll be reading the ID registers all together at once. And then once we are verified here, then we'll be just using the build macros like we used to do earlier as well. So in this way, we can prevent the runtime EL3 exceptions altogether. So if you could see here during context management phase, since this macro has already been verified, validated. So we will enable the feature here, and during restore routines. Earlier we were using the architectural versions to access the registers. So right now we are using the feature specific build flags to providing a controlled access to these registers, both saving as well as restoring. So in this way, it's very much evident that using the build flags, you are using these build flags in all the 3 sections. So getting it validated in early phase is always a, I mean, kind of advantage, and that's what we are doing here. So yeah, regarding state 2, currently we haven't implemented it, but we have some ideas behind it, what we need to do in future. So what we'll be doing is, as I mentioned earlier, in the feature state 2, we will be not doing any kind of checks during boot time. So we will be allowing the platforms to boot, and during runtime, we will be trying to do the checks. And here again, there will be no panic, will not be called here, but the only idea is during, during runtime here, if in case if the feature state is set to 2, and here we'll be checking the feature. If in case if it is present, then only we'll go on enable the feature. If not, we won't enable it. I mean, even in feature state 2, we are trying to avoid the exceptions, but the only thing is this comes with an additional cost. There'll be more if else checks. So yeah, it again depends to the platform. I mean, we'll be leaving it to the platforms how they want to make use of this feature. If they're pretty much sure that they want to make use of one, wherein the software will be less optimized, they don't want to use of this multiple if else checks, they can just proceed with a feature state 1 so that they can get a very optimized software, and they'll be very much secure. I mean, there'll be no runtime exceptions at all. So yeah, this is the plan for the state 2. Moving ahead, yeah. Next thing is, okay, we have faced few issues with the current implementation. I just need to bring that up. But before that, giving a quick recap. So, well, feature detection mechanism, it basically detects both mandatory as well as optional features. TFA in general, it supports majority of the ARM architectural features starting from 8.0 and above. So currently with our present implementation, we have started from 8.0 and above. So we have picked all the features, both mandatory as well as optional. And our existing implementation, we usually, what we do is in the TFA, if there is any new feature, we usually provide a build flag, and then we allow the platforms to take care of that. If they want, let them enable it. If they don't want, let them disable it. So, and then as part of feature detection mechanism, we will bring those build flags and we will validate it. So usually, if in case if it's a mandatory features, meaning if the particular platform is based on some particular architectural version, let's say 8.4. So all the, as per the ARM, whatever features has been defined, stating that, okay, this is mandatory in 8.4 or lower versions, all those things will be present in that platform. So those things will be detected properly. There will be no issues here. So in general, if in case if the feature is mandatory, so detecting those mandatory features will never be a problem. So it will be properly detected and it will be validated. So just an example, if FGT, as per the ARM docs, it's a mandatory feature from 8.6 and above. So we provide a build flag that is enable feed FGT. So which will be set by default from the TFA main makefile itself. We ourselves will be setting it to 1. So from 8.6 and above. So, and then this particular build flag will be brought under the feature detection mechanism. And this will be validated properly because obviously it's a mandatory feature. It will be present in the platform. So no issues here. So that's what.
So this is, sorry, a quick question. Is this based on the ARM Arch version macro? So based on that, you will do enable feat FGT or whatever, for example?
Yes, enabling the feature flag, yes. In the main makefile will be based on the architectural versions, yes.
Okay, so architectural version will be used to enable all the mandatory feature flags.
Correct, yes.
Okay, thanks.
Okay, so yeah. So, just giving you an example, what would happen if in case if it is a mandatory feature and what would happen if it is an optional feature? And then I will drive you people with the issue what we are facing now. So yeah, since FGT is a mandatory feature from 8.6, and if a platform is based on 8.6 version, it will implement it and this feature will be detected. It will be present in the platform. So no issues here, meaning the feature FGT, if in case, for example, if the platform is based on 8.5, then this feature FGT will not be enabled by the TFA because we will be, obviously there'll be one-to-one match, with the platform as well as with the TFA build, whatever we will be building. So usually there'll be no issues here. There'll be usually one-to-one match and we don't find any issues with detecting the mandatory features. So moving ahead with the optional features, yeah. Similar to the mandatory features, how we have provided the support, we usually provide the similar support for the optional features too. Providing an explicit build flag. The only difference here is we usually don't enable the optional features within the TFA main makefile. We will disable them and we will allow the platforms to decide whether they want to enable it or not. Because based on their platforms, they will be very much sure whether the optional features are present in the platform. So we ourselves from the TFA will not be enabling it. So Coming to the detection part, yes, even in the under the feature detection mechanism, we will be bringing the optional features too. So explain some corner cases here. So let's say feature NV2 nested virtualization support, which is an optional feature from 8.4. It is supported in TFA. And since it is an optional as per ARM, TFA implements and disables it. So what would happen if we bring this particular feature under the feature detection mechanism? Here, we are pretty much sure that if this flag is being enabled only, we will be detecting it under the loop. If in case if the flag is itself is disabled, we will not be reading any ID registers, and we will not be validating it at all. So here once again there will be no break in the boot flow in general, but there is some minor deviation in the way this has been handled for a couple of features in our existing code base. That is with SPE as well as with SPE, statistical profiling extension as well as scalable vector extensions. These two features, they are optional features, but somehow in our existing TFA code base, these are implemented as well as they are enabled by default within the TFA main makefile itself. So this is one deviation with the general implementation what we used to follow. Usually we don't enable the optional features, but we have done that. So the problem what we are seeing here is, as I said, the feature detection mechanism, it will run through all the features. It won't, discriminate, or won't consider whether it's a mandatory or optional. So now with feature SPE and SPE being considered here, wherein in our TFA main system, we are enabling it from ourselves. What would happen is SPE and SPE will not be present in all the platforms since they are optional features. So since these are enabled from our main default build system, during runtime, when these features are getting detected, since they're enabled from the TFA main system itself, so this will be validated. And once we validate it, we usually get, a wrong value, or the ID register returns a different value stating that these features are not present. As a result, the boot flow will be halted because these two features are optional. They should have been disabled, and we should have allowed the platforms to decide whether they want to enable it or not. But somehow this has been deviated with the existing implementation. So as a result, if I bring these two features under the feature detection mechanism, it will halt the boot flow for certain platforms who are making use of this feature. So, but again, in order to comply with the feature detection mechanism, ideally they should be disabled from our TFA main build system, and we should allow the platforms to enable them. But the thing is, we have already written a cover note to all our partners, and we have sent an email stating this because we are not sure which all platforms will be affected if in case altogether, if we disable it from our main makefile, and if we, then allowing the platforms to enable it. So our main question here is, we will be disabling it in future. So we want our partners to be aware of this so that they themselves should be enabling it based on their requirements. So we need the input from the platform owners here. Actually, we try to push a patch wherein we ourselves disable it in our main build system and then enabling it in the platform specific makefiles. But again, during the code reviews, we felt that we first need to inform this to our partners, take your feedback on what you feel if in case if we disable these features from our main build system. So yeah, this is one thing we have encountered so far. So these two features. So please take a look at this. And not soon, but in the upcoming days, we have a plan wherein we will be disabling these features in general, and we will be allowing you people to take the decision. So yeah, that's one thing we need to convey through this presentation today. And yeah, in general, the note for all the TFA platforms. So as I mentioned just now, the scenarios wherein if the optional features are enabled by default from our main makefile, it would cause, stopping, during the boot flow. So in order to, we just don't want it to break this boot flow altogether. So that's why for now, we have overlooked such features. And altogether, we are introducing this as an experimental procedure by introducing a feature detection build flag, wherein we want you people to enable it, get used to its behavior, and also if you have any feedback, if you feel this can be still improvised or whatsoever, if you feel, please feel free to and reply to our emails or you can ask any, you can send us any suggestions. But for now, as part of 2.7 release, we are introducing, I mean, we have already upstreamed this implementation and we are introducing this as an experimental procedure. So for now, there won't be any, stopping in the boot flow for with your platforms. It will still, it will be still working as fine. But soon, I mean, we have provided some time window for you people to decide on it. And if you have any feedback on this, or if you feel like the SPE and SVE should be enabled by default, and you don't want to take any decisions on that, please do let us know, where we can again decide on that. Or if you're okay with the decision, what we will be taking further, like we will be disabling it in our main build system, and we will be allowing you the decision to make it. So just state your opinions through the emails. So yeah, we're happy to hear feedback on that. Yeah, other than that, the only thing we need to update you is currently we are in phase 1 delivery, wherein we have covered most of the features starting from 8.0 and above, wherein for state 1, we have covered most of the features, remaining some exceptional cases as the one which I mentioned now. So our plan is to, cover the state 2 as well as these exceptional cases in the upcoming days. So the patches are already upstream and you can find it in these links. And also we have provided the complete documentation, what this is all about and how our partners will be benefited from this. So yeah, that's it. So that's all I wanted to convey today with the feature detection mechanism, what it is all about, how it would help our partners as well as in general to any user who wants to make use of it, to get assured whether they're properly set the build flags or not. And to mitigate the runtime exceptions, we are bringing this mechanism. So yeah, if you have any questions, please feel free to ask me here.
Hey, Varun Wadikar here. So one question, in one of your slides, you said that this is currently done in BL31 main.
Yes, yes.
So just curious if you evaluated doing this really early, even before BL3, because there is considerable code that is running, code that runs before BL31 main gets called. I understand you want to protect the context management library here, but
correct, yeah.
If you do that early,
Mm-hmm.
I mean, there might be other scenarios.
You mean to say, you mean to say bringing it in BL1 itself?
No, in the BL31 itself, but before BL31 main.
Okay.
I mean, somewhere in the assembly code. Just a thought.
Okay. Well, our only thought process behind this is like, most of the features, are getting set from the, in the BL31. Yeah. So yeah, we are considered enabling it in BL31 main. Yeah.
Okay. Another question is, you said that they are somehow linked to the architecture version.
Yes.
But there are scenarios where, for example, someone starts with architecture 8.5, and then adds 2 or 3 features from 8.6, 8.7, whatever, but still the base is still 8.5. So how do you think partners with these kind of SOCs should handle the feature detection?
If you could just give any example in general. I mean, for example, you were mentioning like there is a feature which is being mandatory from 8.5.
A feature that is mandatory in 8.6, but the SOC is version 8.5 itself and just uses one feature from mandatory feature from 8.6 or 8.7, 8.9, whatever.
Yeah, some of the speculative vulnerability features, I believe, are backported or allowed in lower ARM versions. Is that what you're talking about, Varun?
Yeah, I mean, it can be anything. Speculative is just one example.
Yeah, it can be anything. Yeah. I think.
So, I mean, I just
definitely those were.
Yeah, just a generic question, because yeah, I mean, we do have situation where something like that happens. I just want to check, how partners like us, how they should go about enabling the feature detection in that case.
I'll just rephrase your question because in between a few words were missed. So I'll just rephrase it if you don't mind. So you meant to say there are some your SOC is based on 8.5, but you want to make use of some of the features which are based on 8.6. Am I correct, right?
Yeah.
Okay. So okay. So in that scenario, you.
Yeah, I think we're at a point now where there really is no direct link between the architectural versions and the feature set. The original rule, if I'm remembering right, was that you could go back one version. But I think nowadays there are quite a lot of platforms where, like Baron says, the features are pulled from several versions ahead.
Okay, but in general, I would say, I mean, this particular implementation, what we are trying to introduce right now, it will be like, it will be detecting with respect to the versions, what the SOC supports, for example, till 8.5, whatever the features has been supported from with the SOC. So that will be detected properly. But if in case, if you want to enable the 8.6 feature as well in there, I think in that case, actually, it will halt because your SOC is not supporting, but you are trying to enable one of the 8.6 features. So as a result of which the boot flow will stop there. So there should be one-to-one match.
Sure. I understand. I mean, that will happen.
Yeah.
But I mean, as I said, this is a scenario where.
Okay. I mean, thanks. Because
we get.
Yeah, good to highlight this point because we weren't aware of this. So we usually, I mean, at least with the analysis what I did so far, so I usually compare one-to-one, wherein for 8.5, all the features should be either, I mean, the lower versions or with respect to, I mean, till 8.5 should be detected and they should be enabled. Yeah.
Okay.
So I guess it. Sorry, finish your thought, Varun.
No, I just wanted to say that I would request that you take this feedback and
Sure. Yeah.
make it configurable. Thank you.
Thank you.
So what happens if you set ARM Arch version as major as 8 and minor as 5, and then you enable say an 8.6 feature directly using the flag in the platform? Is that allowed?
Yeah, it's
because
still
I think
allowed.
that might solve this issue.
It is still allowed, but the thing is, if you're, I mean, we internally from our main make system, we will ensure that, okay, fine, if in case if the ARM states a particular feature is mandatory from a particular version, we will enable it from ourselves. On top of that, still, yes, the platforms can go ahead and enable any other feature, even if in case if it's an ahead of that. But I mean, during a feature detection mechanism, we will just detect whether the platform usually supports it or not. If in case it is supporting it, no issues. If in case it is not supporting it, it will stop there itself. Yeah.
So
that seems like it will solve the problem.
So I guess if the platform has enabled a 8.6 feature and the feature discovery, the ARC feature discovery register shows the right values, it shouldn't be a problem, right?
Yes.
Yeah, so the platform is free to enable any additional features that they would like to enable, and at runtime it gets validated, and as long as the feature registers on the ARC feature register shows the right values, it should be fine. Yeah.
I mean, we ourselves, why? I mean, at few scenarios we have seen wherein few platforms have not enabling few features. So from the TFA build system, we want to ensure that mandatory features are getting enabled. But yeah, again, on top of that, if the platforms they don't want, they can take the decision. Yeah. Or if they want any other features, they can still proceed this.
Hi, one question. Maybe I missed something, but this will only run for CPU 0, like the bootstrap CPU, right? The check, I mean.
Yep, that's right. Yeah, it's running in BL31 main, so it's only being validated on the boot CPU. Yeah.
So if there's a mismatch in terms of features, let's say some CPUs have additional features.
Yeah, I think there's a strong recommendation that all the CPUs in a system should be aligned on the feature set. Otherwise, bigger things can go wrong while Linux is running or OS is running. Yeah.
I understand that. I'm just wondering if there could be such a scenario where you have like a high performance CPU which has something extra in, and Linux knows it, or a driver in Linux knows it, and then it only makes use of that feature. Maybe it's just hypothetical, but so maybe it's not even a real scenario. I'm just trying to think if there could be such a situation.
Okay.
Yeah, well, so I know that there's a strong recommendation against building such systems. So yeah, most of all the assumptions that we make in firmware is all the CPUs are SMP, symmetric multiprocessing, same feature set across all the CPUs. And if they differ, then we'll have problems. Yeah.
Got it. Okay.
But I think that's a valid point, and people can still build such systems. So I guess okay. So the thing is, it won't handle for the other CPUs.
Right. Yeah. So we are limited to the common denominator with all the CPUs, right? Like,
I mean, just the boot CPU, I guess.
Boot CPU, yeah. Right.
Yeah.
Got it.
I think this should be added as an enhancement in the future.
Yeah, we'll take your point. Sure. Yeah, we'll think about it, how we can actually still enhance this.
Yeah, but supporting different feature sets for different CPUs, as it's a can of worms. It has a lot of other issues. I don't think we can. It would be a major change in the software architecture itself. So
Even,
all of the
in fact, if you consider higher level software stacks like just Linux, I'm not sure it would be able to migrate threads among core that do not have the same set of features. So I agree with I'm quite sure I've seen some recommendation, a strong recommendation that for big little systems, all of the cores must share the same features. Otherwise, it cannot work.
For normal threads to migrate between CPUs, yes, that's right. But I'm talking about, let's say there's a particular driver which pins a thread to a particular core and makes use of some additional feature. That, in theory, that's possible, right? I agree that might not happen, like that might not be recommended, but in theory, that's possible, right?
Well, I guess that's the harm recommendation to system integrators when they are building chipsets. It's true that a system integrator can just do whatever it wants, but it would defeat this strong recommendation.
And why add complexity for a use case that does not exist, right? Or if there's a real use case, I think it might be worth revisiting. Otherwise, it sounds complicated to add that. And yeah, from a security point of view, you don't want to keep adding complexity for no reason in EL3.
Actually, there is an NVIDIA platform out there which does this already. We have two completely different CPUs part of the same SoC.
Right, different CPUs are okay, right? But they should have the same baseline feature set. Do they have different features?
I think I will have to go back and check, but I mean, they're architecturally different CPUs. So I started with Xavier SoC. It's already there.
When you say architecturally different, like ARM and RISC-V kind of different, or do you mean like ARM 8.4 and ARM 8.0 different?
Yeah, the ARM versions, they are still both ARM CPUs, but architecture, the version of the architecture is different. I have to go and check what the minor version of both of them are, but I mean, so the point is we already have one platform out there.
Right. So
That's
I guess there are multiple options here. One option is from the firmware point of view, enable it, make it dynamic. So every time a core comes into BL3, when it detects whether the feature is present or not, and then does the appropriate thing. The other thing is if if the feature doesn't need any special handling in EL3 or secure world, say like pointer authentication or BTI, then firmware doesn't need to be involved at all. So in such cases, I know it's a firmware can be built without knowledge of these features, and it's up to the non-secure software stack to prevent migration of threads and do it in a custom way. Yeah.
Yeah, I think a feature state 2 will address that, right? So that should be fine.
Possibly, yeah, but I don't know whether all cases can be catered for. Yeah, there might be some built-in assumptions. We might update some global state based on the primary CPU updating some feature flag, and then yeah. But in most cases, it seems it might work, but can't say whether all cases will be covered.
Yeah, I think if if the additional features in other cores are such that they're basically just additional features, they don't conflict with the common features with other CPUs, then I think feature state 2 should be fine, right? That's just something on top. It doesn't conflict with any of the existing features which are common with other cores.
Yep, should be fine.
Yep.
But given that there's a strong recommendation, this is not an assumption that we would normally make when designing software and firmware. We would go with the assumption that all the cores are symmetric. Yeah.
As a reference implementation, I guess we're going to look to try to support the most common general use cases. If over time, one of these types of systems, becomes more common, and people don't want to support that downstream of the reference implementation, you always have the options to upstream optimizations and things like that for possible integration. I think trying to cover every case and every possible future case and anything that we can think of right now might be a little bit difficult to achieve. So I think we're trying to, as Toby said, the general recommendations we're trying to support, and as partners, explore other areas. Then of course, we're more than open to take contributions. If if you find something downstream that you want to try to support upstream.
Yeah, sounds good. Thank you.
Any more questions for Jayanth and more discussions?
Yeah, one question for feature the value equal to 2.
Okay.
Will there be a warning message saying that this is something that we found, it's not enabled, and we are skipping all the future accesses?
I mean, we are not providing any warning message as such. We will just, check and we'll just move on. If in case if the feature is present, we will do the enablement, or else no, we will just don't do the enablement. No warning message as such.
Sure, but do you think? If you add a warning message, it would be helpful for the platform to say that okay, accidentally this was enabled, needs to be disabled, and this we already have such warning messages for erratas.
Okay.
So maybe something like this would help. And because that for erratas, it is definitely helpful. We see that, this is enabled, but we see the warning message. So we go ahead and then try to fix the problem.
Okay, yeah, we'll consider that, sure. In the phase 2 implementation, we will take that into consideration, sure.
Thank you. And the entire feature can be completely removed from the binary by disabling the feature underscore detection macro. Is
Yes.
my understanding correct?
Yes, yes.
Okay.
The only thing is like in future, we will be enabling this feature detection mechanism. I mean, by default, it will be 1, but that is once the entire, I mean, all the 3 states are completely implemented.
Sure. I mean, the only reason why I asked is because, I mean, during early development, something like this is definitely helpful. But once we know that everything is stable and we are ready to production, we might want to disable it.
Yeah. Any more questions?
So if people do have more questions, I think it was Manish who posted a mailing list about this feature a short time ago. So we could always follow up any further discussions around that mailing list discussion where the feature is described in more depth. Manish Pandey, that was who posted. It was Manish, wasn't it? It wasn't yourself.
Correct. Yeah, Manish Pandey. Yes.
So if you look for that in the digest and wish to reply to that, we're happy to take continue any discussion on the mailing list, or just start a new thread if necessary.
Yes.
All right, thank you, Jayanth, and everyone. We're more or less just short of the top of the hour, but if there's nothing else to discuss on this, I will take the recording and make the slides and everything available in the next few days in the normal place in trustedfirmware.org.
Sounds good. Yep. Thank you all for joining the presentation. Yeah.
Yeah. Thank you, everyone. I'll stop the recording.